Welcome back to my course on climate science. This is the third lecture, and this is going to be a continuation of our discussion of climate basics. Let me just share my screen here so we get to where we are. Very good. So we have been looking at the big factors that drive the climate. We spent the first part of this section talking about radiation balance, and then we talked about the general circulation patterns of the atmosphere and of the oceans, driven by the fact that the Earth is a sphere and that it spins. And a little bit about cooling and heating of the oceans relative to the land, because what we know is that the water heats up a lot slower. It has a higher heat capacity than the land does, and that general circulation moves energy, tries to move energy from the equator to the poles. What we're going to talk about today is factors that get us closer to the weather. So we're going to dive down a little bit in scale. We're going to go to smaller scale, scale being the spatial scale. We're going to go to smaller scale, well, actually the temporal scale too, smaller scale phenomenon that occur on the surface of the Earth. This is sometimes called the turbulent cascade, because as you move down in scale, you run into more variability, local topography, local influences of water, large bodies of water, and so on, make a bigger difference. And you could even get down to the scale of microclimates. You know, if your house is at the bottom of the hill and the guy's house at the top of the hill, the trees blossom sooner than yours, or something like that. These things are real effects. So in this smaller scale, we're going to talk about air masses, fronts, and clouds. And a little bit about how they work so that we have a little background on these things. The land, this simple statement that the land heats up faster than the water is kind of observed in this. This is a picture, a NASA satellite observation of pressure. And what you see out here in the Atlantic and the Pacific are high pressure regions relative to the continent, North American continent. And if you remember our three-cell model, we would expect high pressure to be around 30 degrees north, which is sort of, and up to, you know, moving further north from that in the Ferrel cell. And you see some of that here, but what you also see is you see that the North American continent is lower pressure, which is a little bit of a variation in the three-cell model. This is a summertime measurement with a fairly hot July. Pressure is coded as the red, higher pressure is red colored. So you can see the effect there. And this happens and is a variation in the three-cell model. If I go to the next slide, this is a average annual atmospheric pressure at sea level and with some surface winds drawn on it as the arrows. It's basically a simulation, but it shows the effects of the continents and the seas, which modify the three-cell model a little bit and create different more local weather patterns. Now, if you look in the southern hemisphere where there's not as much land, you get a better representation of the three-cell model. So start down at the bottom of the slide. Again, high pressure is more in the red-brown end of the spectrum. So you get the high pressure you expect at the pole, then the lower pressure moving north, high pressure again at about 30 degrees, you know, 30 to 40. Actually, it shows about 20 to 40 because this is probably a summertime thing. And then you get the equator, which is low pressure again, right? You can see the ITCZ, that's the convergence of the wind arrows from the northeast and from the southeast converging on the equator that runs across northern South America. But as you go north, you get the high pressure you kind of expect, but it's even stronger over the, at 30 degrees north, but it's even stronger over the oceans, right? And then you see some land masses further north where there's some high pressure points and some low pressure points. So although you see the 3-cell model, it's modified by these land ocean effects. And that will have an influence on more regional climate things, climate experiences that occur in those areas. The next thing we want to talk about a little bit is air masses. Air masses are, or sometimes called air parcels, but they are parcels of air, and think of these as a large region of air near the surface that has similar temperature, pressure, and moisture content. And the way it got that content, it was in contact with the land and the ocean, and the surface properties were sort of transferred to the air parcel, and then it moves as an air mass driven around by the general circulation of the atmosphere. And what you can see here, we've labeled these. These are very general labels, but they refer to air masses which tend to have certain properties. So continental polar, as you can imagine, is going to be cold, probably dry, because cold air doesn't hold a lot of moisture, and it's over the continent that it equilibrated, so it's equilibrating with land. You have an Arctic air mass, it's going to be very cold. You have marine polar, which means these are air masses formed over a cold part of the oceans. Marine tropical, which is likely to be moist, warm air. Continental tropical, which is likely to be dry, warm air. And these air masses get pushed around. When they run into each other, they form what's called a front. And you've probably heard, if you're thinking about, if you're watching the news or something, the weatherman will talk about cold fronts and warm fronts. Here is a case where, in this picture, an air mass number 2, which looks like it's probably a marine tropical air mass, is being approached by a cold air mass from the north, probably a continental polar air mass coming down from, let's say, Canada someplace. And the two are, there's a front formed. This is actually a cold front probably, because you see just to the northeast of Texas, you see clouds forming where these two air masses are running into each other. And so we suspect that the cold air mass coming from the north is pushing under the warm air mass from the south and causing the that air parcel to rise. And since it has moisture in it, it's going to eventually reach the saturation pressure and condense and form clouds. And so fronts are where air masses come together. And one of the things that's always a little bit confusing is if you had a cold air mass running into a warm one, or a warm one running into a cold one, which one is the cold front and which one is the warm front, you might ask. And it really comes down to which air mass is pushing more aggressively. Typically, or by definition, cold fronts are places where the cold air mass is pushing against the warm air mass and causing the warm, moist air to rise, usually forming clouds. There are other ways for clouds to form by lifting, but this is a very common way. A warm front is kind of where the warm air is moving and it's going over the top of the cold air. Usually it's not a vigorous lift, it's a slower lift. And you can get sort of regional clouds forming, but not typically storm clouds and that kind of thing. You'll see at the bottom here, there are symbols for cold front, which are the sharp, pointy things. Warm front, more like the top of a sinusoid, a smooth curve. Occluded fronts. An occluded front is one where there's been a some kind of cyclonic motion of the cold front, and a warm air got trapped between two pockets of cold air. So occluded fronts are typically places where warm air is rising very aggressively. Stationary fronts are places where, let's say, the wind is blowing parallel to the front, so you don't get them moving. One front isn't pushing hard on the other one. It's kind of, both of them are kind of just sitting there, so to speak. That won't last for long, but it happens. And if you're watching your weather channel, you will see this kind of picture often down in the lower right corner over, looks like Georgia or somewhere where there, you see a low, and that low is being formed by a circulation, which is called an extratropical cyclone. Extratropical cyclones form along fronts. They are an instability that basically causes rotation. And we won't get into the meteorological details here. They're not important for our course. But you get a rotation of the cold and warm fronts that with a low in the middle. And the low causes ascending air. The low is caused by ascending air, so you get some convergence of flow into the center, causes air to ascend, causes a low to form. The rotation tends to push air up, which usually, since it's a front, there's a warm air around, and that causes a storm because you get air rising quickly, forming clouds, and usually front. These extratropical cyclones again get pushed. You notice the high out to the west of this front, of this low front, and the high is going to push, is probably pushing that low front in the ferrule cell. And that low front could be a snowstorm, it could be a heavy rainfall, depending on where it goes as it moves north. Now, these extratropical cyclones don't last a long time. They may last a number of days. They don't care whether they're on land or at sea, unlike a tropical cyclone like a hurricane, which matters. When the tropical cyclone gets over land, it tends to dissipate. But the extratropical cyclone here will move to the northeast. You see the symbol for an occluded front there. That means the cold front has swung around and trapped warm air between it and some of the cold air that was in front of the warm front before, causing the warm air to rise aggressively. Okay, so that's a picture you probably see on the news a lot. You'll also notice that the lows have the contours close together, the pressure contours close together, showing a rather spatially sharp drop in pressure, whereas the highs are wide, or more open, smoother pressure contrasts, which tend to cause nice weather. Okay, so this is a quick kind of drawing of the circulation around the low. This kind of circulation applies both to an extratropical cyclone as well as to a hurricane or a typhoon. But the idea is, if you have a low, the pressure gradient force, as is drawn here, the FPG, is trying to push air into the center of the low. It turns out the Coriolis force is trying to pull in the opposite direction, and so it turns the flow line to the right, and you end up with flow around the low, and ascending air in the center, up through the center of the low. And as I said, they behave differently whether they form along fronts in an extratropical region or whether they form in the tropics. A hurricane is basically a hole in the atmosphere. It's kind of an interesting way to think about it. But they form over a warm spot in the water and then move to the east, as we've discussed, as we will discuss a lot later on in the course. Now, the way clouds form are somewhat important for us later on in the course to know a little bit about clouds. Again, I'm going to go into a little bit of detail here. It's not necessary to know all this, but just to there are some lines on this graph. So the vertical axis is altitude, and the horizontal axis is temperature. And what you can see is these lines on this graph are all tilted so that they show cooling as you go up in altitude, right? So the one that's labeled the DALR, we'll start there. If you have a parcel of air in contact with the ground, and let's say you get a particularly hot day, the ground heats up, that parcel of air will start to rise. And of course, it's at sea level when it starts, or some altitude like sea level when it starts, and it starts to go up in the atmosphere. As it goes up, the pressure reduces, so the parcel expands, and it cools. And it cools along the line called the DALR. That stands for dry adiabatic lapse rate. It's kind of a lot of words that aren't that describe some of the process. Basically, adiabatic means that as it cools, it doesn't exchange air with the surrounding atmosphere. That's a pretty good approximation because there's a different density for the most part, and so it's not going to exchange much energy with the surrounding atmosphere. And the lapse rate just refers to the if you want to say colloquially, the lapse in temperature or the reduction in temperature, right? And it's dry because the parcel doesn't have moisture in it, right? Now, that rate of cooling can be calculated from basic physics, basically having an exponential decrease in the pressure of the atmosphere that it's rising in and conservation of energy. So it tends to, the dry adiabatic lapse rate tends to be about 10 degrees centigrade per kilometer. And now what you should also know is the ELR is the environmental lapse rate. That's the name basically given to the rate at which the atmosphere actually cools at, right? And the atmosphere tends to cool at 6 or 7 degrees centigrade per kilometer. So these two lines are going to cross someplace. And what that means is that as the air parcel rises, it quickly reaches a point, or maybe not so quickly, but it reaches a point where its density starts to be the same as the atmospheric density, right? Started out, it was less dense because it had been heated by the surface, and as it goes up, it cools and expands, but it cools at a rate faster than the environment that it's in. And so it reaches a point where it can't rise anymore because the surrounding air is about the same density as it, or the surrounding air is beginning to be less dense, and so it's not going to rise any higher. Now this gets a little more complicated if that air parcel is not dry at the surface. So let's say it has some moisture in it. It starts to rise up along the dry adiabatic lapse rate, but it gets to a point where it's the saturation vapor pressure, that is the point at which it's cool enough that it will start to condense. So it starts to condense water from liquid from the water vapor. And when it does, the condensed water has less energy than the water vapor gas had before. And that energy has to go someplace. And what happens is it goes into the parcel. So it goes into the parcel and heats the parcel. So as the moisture in the parcel condenses, it heats the parcel. And the moment that condensation starts, the parcel starts moving along a something called the MALR, the moist adiabatic lapse rate. Sorry, I get all tongue-tied here. The moist adiabatic lapse rate, which lets it go even higher than it would if the parcel was dry, right? That's basically what we need to know. So this can go very high. Of course, it can't go higher than the tropopause, because when you get up to the tropopause, the temperature is staying about the same, and then at the stratosphere, it starts warming up. So it can't go higher than that. But it can go pretty high up into the atmosphere. So in summary, if you think about what's happening at the ITCZ, we talked about the ITCZ, that's the intertropical convergence zone at the equator where clouds are seen forming. If you think about what's happening there, air is rising. It's moist air because it's an air mass forming over water, and it rises and expands. And obviously, as condensation occurs, it rises even higher and ends up carrying a lot of latent heat with it up into the atmosphere. Okay, and finally, we're going to talk about the tilt. So the Earth's tilt causes the seasons. This is pretty common knowledge, I guess. And the idea is just that when the northern hemisphere is tilted towards the sun, when we're in that part of the orbit where that happens, it receives more energy per unit area, and we get a summer season. Obviously, at that same time, the southern hemisphere is tilted away, and it gets a winter season. And the same thing occurs vice versa. Of course, even if you're in summer in the northern hemisphere, you're not necessarily, because the Earth's orbit is elliptical, you're not necessarily closest to the sun, but depending on where you are in the orbit. But that is the effect, and it speaks to the importance of the angle, the sun's zenith angle to the surface of the Earth, that it can cause a season. So let's just do a quick review of this whole business of the basic climate effects by answering our climate questions. We know that the difference between weather in Tallahassee and weather in Rochester, New York, at least the temperature of the climate, is largely due to the spherical shape of the Earth, causing a latitude difference in the amount of energy that's received in those places per square meter. We know that Columbus came to America on the trade winds, and we understand that the trade winds are basically formed roughly out of this 3-cell circulation system, because the energy difference between the equator and poles tries to push energy to the poles, and the spin conspires to make this 3-cell model, where Columbus can sail over on the easterlies and sail back on the westerlies, although he didn't do that on every trip, but tried to take advantage of that. We know that hurricanes form over warm air, where you get ascending air, creating a low pressure system. That low pressure system causes a rotating system that drives energy up into the atmosphere. The low moves north and west, driven by the trade winds, until it gets far enough north, or it's steered by a high pressure by a high pressure ridge or something like that, some piece of circulation that's a little different, and basically ends up in the westerlies to drive it back into the Atlantic Ocean, where usually by then, if it's over land, it gets pretty much becomes a tropical storm, but sometimes it can still be a hurricane in the Atlantic Ocean. And we also know that Dallas is largely has a largely different climate than Los Angeles, because it's an inland city. It's subject to air masses coming from the north, cold air masses coming down along the Rocky Mountains through the Midwest from Canada, that can bring snow and cold weather into Dallas. It's also subject to marine tropical air masses from the Gulf that can be very hot and humid. If you talk about Los Angeles, the California current, first of all, it's a coastal city, so it's moderated a bit by just being close to a body of water that doesn't change temperature very quickly. But second, there is a California current that's part of the general circulation system that moves along the California coast and tends to keep the West Coast more temperate. And in summary, for this whole section, for these first 3 lectures, we can say that we've now got a sense for these big factors that drive the climate. The radiation balance between the sun and the earth, the effect of the earth's spin and the spherical nature of the earth in the overall circulation, the fact that that circulation is modified a bit by the land and by the relative heat content or specific heat, or the ability of the water in the land to absorb heat being quite different. The fact that we form air masses by the exchange of energy between the atmosphere and the surface of the earth. Those air masses get pushed around by the general circulation and end up at fronts to create various kinds of spinning cyclonic weather systems. Oftentimes those spinning systems lead to the generation of clouds and precipitation. And finally, of course, there's a large-scale moderation due to the seasons which are driven by the tilt of the earth. So that concludes our discussion of climate basics. We will move on to beginning our discussion of is it warming in lecture 4. Thank you for being here.